When the lights go out, plunging cities into darkness and silencing the hum of our modern lives, it's more than just an inconvenience, more than a temporary disruption to your evening plans. It's a stark reminder of our dependence on a system we often take for granted. It's a sign that something significant has happened, a ripple effect, originating from a source often unseen and unknown to the average consumer. Within a vast, complex system, a network of interconnected components stretching across vast distances, all working in harmony to deliver electricity to our homes and businesses. This system powers everything from homes, lighting up our streets and keeping our families comfortable, to hospitals, where life-saving equipment relies on a constant and uninterrupted flow of electricity. And when it fails, the impact is immediate, a sudden and jarring halt to the routines and services we depend on. Traffic lights stop, creating chaos on the roads and potentially endangering drivers and pedestrians alike. Hospitals rely on backup generators, kicking into gear to maintain critical functions, but even these have limitations, and even water supply can be disrupted, as pumping stations cease to operate without power, impacting sanitation and daily life. A blackout isn't just darkness, it's a cascade of consequences affecting every facet of our society. It's a disruption of daily life, forcing us to adapt and improvise in the absence of the conveniences we've come to expect. Sometimes with serious consequences, demanding immediate action from emergency services and highlighting the fragility of our infrastructure. The engineering behind keeping the lights on is a marvel, a testament to human ingenuity and our ability to harness the power of nature. A delicate balance of supply and demand, constantly monitored and adjusted to ensure a stable and reliable flow of electricity. But like any complex system, especially one as vast and intricate as our power grid, it has vulnerabilities, points of weakness that can be exploited by natural disasters, equipment failures, or even human error. Understanding blackouts isn't just for engineers. It's a matter of public awareness and preparedness. It's for everyone who relies on electricity, which, in today's world, is virtually everyone. It's about appreciating the science and scale of the grid, the sheer magnitude of the infrastructure required to power our modern lives, and why it sometimes fails, despite the best efforts of engineers and technicians to maintain its integrity. So, let's illuminate the science behind these outages, shedding light on the complex processes that govern our power supply, and see what really happens when the power goes out, from the initial spark to the eventual restoration of electricity. Consider this your backstage pass, your exclusive look behind the scenes. To the world of power grids, a world of intricate technology, dedicated professionals, and the constant quest for a more reliable and resilient energy future. The power grid is like a superhighway for electricity, connecting power plants to homes and businesses through a complex web. Power plants generate electricity using sources like coal, gas, nuclear, hydro, wind, or solar. Transmission lines carry this energy over long distances at high voltages. Then substations step it down for local distribution. Most grids are interconnected, allowing regions to share power for efficiency and reliability. But this interconnectedness means a problem in one area can ripple across the system. Every part of the chain must work perfectly. Generation must match consumption at every moment. Too little power, things shut down. Too much, equipment gets damaged. It's a high-wire act, performed 24/7. Science makes our electrified world possible, but also vulnerable to chain reactions. That's the delicate balance of the grid. Our modern world hums with electricity, a constant flow of power that we often take for granted. But behind the scenes, the electrical grid is a complex and delicate system. A seemingly insignificant glitch in this vast network can trigger a major blackout, plunging cities into darkness and disrupting countless lives. It's a phenomenon that unfolds like dominoes falling, one event setting off a chain reaction with potentially devastating consequences. This is called a cascading failure, a sequence of events where the failure of one component leads to the failure of others, creating a ripple effect throughout the system. It often starts when one piece of equipment fails, perhaps due to a malfunction, an overload, or even an external factor like a lightning strike. When that happens, the load, the demand for electricity, shifts to other parts of the grid, placing additional stress on the remaining components. If a critical transmission line, the highways of our electrical system, or a vital generator, the source of our power, goes down unexpectedly, the electricity automatically reroutes through alternative pathways, seeking the path of least resistance to meet the demand. This sudden surge of power can lead to overloading nearby lines, pushing them beyond their designed capacity. These lines, robust as they may seem, can only handle so much current before their physical limits are reached. Exceeding that limit causes them to overheat, potentially leading to sag, damage, or even catastrophic failure. Each new failure adds stress to the remaining components, further destabilizing the grid and increasing the risk of further failures. This creates a dangerous feedback loop, where each failure exacerbates the situation that can spread rapidly across the grid, leading to a widespread blackout. To mitigate these risks, engineers build in redundancy, designing the grid with backup systems and alternative pathways. However, sometimes the initial event is simply too big, overwhelming the built-in safeguards. Or too many things go wrong simultaneously, creating a perfect storm of failures that the system cannot withstand, all at once. It's like having a spare tire in your car, a valuable resource in case of an emergency. It's great for dealing with one flat tire, allowing you to get back on the road quickly. But it's not much help if you suddenly find yourself with 3 flat tires at once, leaving you stranded. That's how a seemingly small local problem in one part of the grid can quickly escalate and lead to widespread blackouts affecting millions of people. The grid's interconnectedness, while essential for efficient power distribution, is both its strength, allowing us to share resources, and its inherent weakness, making it vulnerable to cascading failures. In this intricate web of power, one seemingly insignificant glitch can set off a devastating chain reaction, reminding us of the fragility of the system that powers our lives. When wires get overloaded, they heat up. The flow of electricity generates heat due to resistance within the wire itself. This is a normal phenomenon, but excessive current amplifies this effect dramatically. With too much current surging through them, the wires can sag due to the increased temperature, causing thermal expansion, or even short out, creating dangerous sparks and potential fire hazards. The integrity of the lines is compromised, making them vulnerable to further damage. If a line sags and touches something it shouldn't, like a tree branch or another conductor, it causes a short circuit. This unintended connection provides a low-resistance path for the current, leading to a sudden and massive surge. To prevent catastrophic damage to the grid and equipment, protective devices like circuit breakers and fuses are designed to automatically disconnect the affected line, isolating the fault and preventing further escalation. However, this disconnection can worsen the original problem. The sudden loss of a transmission line forces the remaining lines to carry the displaced load, potentially overloading them as well. This load shift can create a domino effect, as the burden is transferred to other lines, risking further failures and potentially triggering a cascading outage across the entire grid. In the control center, operators scramble to reroute power flow, adjust generation levels, and implement emergency procedures to stabilize the grid and prevent the situation from spiraling out of control. But these decisions must be made in seconds, under immense pressure, with incomplete information, and with the understanding that every action has consequences that can either mitigate or exacerbate the crisis. Sometimes, the cascade of failures is simply too fast and too widespread for human intervention to be effective. The automated protection systems kick in, but they can only do so much to contain the damage. The spread of an outage isn't just about lines tripping and disconnecting from the grid. It's a complex interplay of factors that can quickly overwhelm the system's capacity. Crucially, it's also about maintaining a delicate balance between power generation and the electrical load demanded by consumers and industries. If a large power plant unexpectedly goes offline, the grid frequency, which is a measure of the system's stability, begins to drop. If the frequency drops too low, reaching a critical threshold, more generators are automatically disconnected to protect themselves from damage. This further reduction in generation capacity exacerbates the imbalance, making things even worse and pushing the grid closer to a complete collapse. It's a delicate dance, a constant balancing act between supply and demand, where even a small disruption can have far-reaching consequences. And when one part of this intricate system stumbles, whether it's a downed power line or a sudden generator failure, the whole system can quickly unravel, leading to widespread blackouts. That's how seemingly isolated incidents can rapidly escalate and cause outages to spread so quickly, plunging entire cities and regions into darkness. The grid's bodyguards are relays and circuit breakers, constantly monitoring for trouble. Relays detect abnormal conditions, overloads, voltage spikes, or short circuits, and signal breakers to act. Circuit breakers are fast-acting switches that isolate faults, preventing problems from spreading. These devices operate in fractions of a second, minimizing outages. They're deployed throughout the grid, from transmission lines to your home's panel. Most of the time, they handle issues so quickly you barely notice. Without them, the grid would be far more chaotic and unreliable. Relays and breakers are vital but not perfect. Sometimes they fail, due to miscalibration, software bugs, or mechanical issues. If a breaker doesn't trip, the fault can spread, causing larger outages. Hidden failures can lurk undetected until an emergency. Regular testing helps, but some issues persist. And if a cascading failure is too big or too fast, even perfect protection can be overwhelmed. The grid's bodyguards can win battles, but sometimes lose the war. That's the fragility of even well-protected systems. When the grid is under severe stress, engineers use emergency tools like load shedding and frequency control. The grid's frequency is its heartbeat. If generation can't meet demand, frequency drops, risking a blackout. Load shedding means intentionally cutting power to some areas to stabilize the system. It's a tough choice, but better than a total collapse. Frequency control involves power plants adjusting output to keep the grid stable. Some generators can ramp up automatically, others are directed by operators. But these measures have limits: too much load shed or not enough generation, and the system can still fail. When disturbances are too large or fast, even these tools can't stop the dominoes. That's when blackouts become unavoidable. What causes grid failures? Nature, human error, and aging equipment. Severe weather, hurricanes, ice storms, heat waves, lightning, can damage lines and towers. Human mistakes, from operator errors to maintenance slip-ups, can trigger outages. Even a small error in relay settings can have big consequences. Much of the grid is decades old. Transformers degrade, cables corrode, and equipment fails. Maintenance helps, but keeping everything perfect is a huge challenge. Sometimes, even animals cause problems. Squirrels or birds can short out equipment. Most incidents are small, but if they hit a critical point, they can start a cascade. Grid operators battle a wide range of threats every day. It's a constant fight to keep the power flowing. The power grid is an engineering marvel, but also fragile. Blackouts remind us how dependent we are on reliable electricity for everything: healthcare, communication, transportation, and more. As demand grows and we add renewables, managing the grid gets more complex. Making the grid stronger and smarter is essential. Modernizing equipment, adding redundancy, and deploying smart technologies. Advanced sensors, automated controls, and better communication make the grid more resilient. Energy storage, like big batteries, helps smooth out renewables and provides backup. Ensuring reliability is a shared responsibility. Governments, utilities, engineers, and consumers all play a part. By understanding the grid's complexity, we can support efforts to build a more robust system. In our electrified world, a strong grid is about